All right, so let's start. So hi everyone, welcome to I believe the ninth talk of the SPML seminar. And today our guest speaker is Chaowei Xiao, who will talk about socially responsible machine learning. So super excited to hear more about the topic. A bit about our speaker, as you just heard, he has moved to Arizona State University. Previously, he was a research scientist at NVIDIA Research. He obtained his PhD degree from computer science department at the University of Michigan, and before that obtained a B from Tsinghua University in 2015. One of I think the research work on adversarial attacks, I believe, that was on display in the Science Museum in London. Hopefully, yeah, some of you may have even visited that. I've seen that in person. And yeah, his work has received Best Paper Awards at Modicum 2014 and ESWN in 2021. Looking forward to your talk, Chaowei. So
yeah, thanks for the kindly introduction, and thanks Wakash to invite me for this talk. I'm so excited to share of our recent progress on the tiny step towards socially responsible machine learning. So with the advances such as the large model, faster computational power, and bigger data, significant success has been achieved for the deep learning models. So we all know deep learning is very good. It has been used in many applications, such as the safety critical applications on a driving system, and also even the privacy concerned application, healthcare, face recognition, to make our life better. Taking the visual recognition as an example, when the task has been evaluated on the standard test data, such as the ImageNet validation dataset, which share the similar distribution of the training data, the performance is getting saturated on these days. However, in the real world, the distribution of the test data is dynamic and not perfect. It does not strictly follow the same distributions. For instance, we may meet the domain shift, challenging data noising, imbalanced distribution, and so on. All of this challenging the model's robustness of the current deep learning systems. We need to take more care of this robustness issue, since it indeed will introduce the severe security problems in our real life. For instance, the autonomous driving vehicles rely on the deep learning to detect the cars, lines, and other obstacles. However, in 2016, there is an accident caused by the autonomous driving cars and killed one person in Florida. After the investigations, the cause of this accident is the autonomous driving system is not designed to always detect vehicles cutting in from with a left turn. Moreover, we may meet the adversary environment where bad guys are behind the machine learning systems to manipulate the data to cause the severe consequence. For instance, we could put the stickers for the traffic signs and even put adversary object on the road to mislead the AV systems. For example, in this example, we can see that for normal box, the autonomous driving can detect, oh, there is a bounding box here, but if we put an adversary object here, we can say there is no bounding box detected, so the car will directly run into this object. And even for the robotic systems, we train our RL systems, and we put a sticker here, we can say it can also mislead the agent to run towards the wall. So all of this shows that the current system is not robust. We really need to care more into the robustness and the security problem of the deep learning systems. Additionally, as I mentioned before, deep learning is also applying into the privacy preserving application, privacy concerned applications such as medical domains. Therefore, how to preserve the privacy in practical is also a really important problem towards the socially responsible machine learning systems. Beyond that, there are also social problems of the current deep learning systems. Taking the language model as an example, it could generate the undesirable behaviors. For instance, it will generate the hate speech challenging the social impact of the current systems. So in this talk, I hope to discuss in just a tiny step towards the social response machine learning systems from these three aspects. Note that these three aspects are not the only things for building the social response for machine learning systems. For instance, many other perspectives such as transparent, fairness, human factor policy, and so on are all really important aspect towards the socially responsible machine learning system. But in this talk, I will mainly talk about these three aspects with the focus on the robustness and the security side. So let's first think about the robustness and the security part. So as I mentioned before, the real world data is imperfect. Thus, to study the robustness of the ML models, many robustness benchmarks have been proposed, such as ImageNet-C, ImageNet-R, and ImageNet-A, and so on. So the settings is like we train the models on the clean images on the standard training set, but we require the models to be robust against these robust benchmarks, which share the different distribution of the training data. So it is like a zero-shot robustness scenarios we discussed today. So in order to think about the ways to solve it, so let's put the machine learning models into the context and study what does a standard machine learning model pipeline looks like. So usually it's like a standard pipeline contains the training steps. Given the training data and the model architecture, we can design an algorithm and loss functions to train the models. After we train it, then we could deploy it to the systems and influence the arbitrary input. So therefore, to solve these problems, so let's view this like aspect one by one. So first, let's think about the architecture side. Because the robustness benchmark has been proposed, so it provides us opportunities to directly evaluate the performance of the current deep learning models looks like on this robust benchmark. So we hope to answer the question is how well do the current DN models performs. So by conducting experiment, we observed that the VIT vision transformer achieves a better robustness compared with the other pipelines. So for example, for the VIT model, we can see the clearly clustering of this object. And even for the semantic segmentation, the transformer is like a vision transformer backbone. So we can see that compared to the CNNs, we can see the clear regions clusterings for it. So such conclusion has been also drawn by many other works in the literatures, but all of these works are mainly from the empirical perspective to study it. So in this talk, we want to dive deeper into the why the vision transformer can achieve this robustness. We hope to have a more systematically study of it. So our journals begins with two well-known research areas like visual grouping and the information bottleneck. So in the next few slides, we will show how the self-attention design, which is the core component for the current vision transformer backbones. We want to see how the self-attention design and the robust generalization of the vision transformer models interestingly equal this classical task. So let's first see the visual grouping. So visual grouping consists to group the pixels into the part and object. It is a core function of the human visions that bridge low-level and high-level visions. Before deep learning areas, visual recognition is dominated by the visual grouping. Among these methods, the most classical one is the graph cut. For the graph cut, the most commonly used method is the spectral clustering. It has the nice property that it's robust against the noise and obtained the compact code. So if we compare the formulation of the self-attention and the graph cut, it's not hard to see the similarity here. Indeed, recent vision transformers also shows the interesting properties such as emerging meaningful segmentations. Motivated by these phenomena, we conduct an experiment and show the strong correlations between the grouping and the robustness. So we began with the observation that the meaningful cluster emerged on the VIT tokens features. We examine such phenomena using the spectral cluster. So we conducted the spectral clustering on the the features from the vision transformers. Since the number of if we see these images, we can show that we do the spectral clustering, so we can evaluate the egg values. So the large egg values means the cluster group, and the 0 or tiny egg values means that there is some major clustering. So when we see these figures, we can say that for the vision transformer blackbones with the layers goes up, the number of with the layers goes up, the clustering has been formed. So where the grouping start to form, so the robustness is also increased significantly. So by viewing these visualizations of the attentions features among the different blocks in the vision transformer, we can see that after some middle layers, we can clearly see the grouping of the object. So here is all the classification task. So we do not do any segmentation. But interestingly, we can see that this grouping phenomena comes up. So that is shows that why the vision transformers achieve the robustness. So we combine the visual grouping with self-attentions. And also we feed the Gauss noise into the current vision transformer backbones. And we also find that the resulting perturbations measuring by the normalized feature norm decrease rapidly together with a number of significant egg values. So such observation also indicate that the grouping and the improved robustness over the middle blocks, it further verify our findings. Another aspect to understanding why grouping happens is that the self-attention promotes the formation of the information bottleneck. So we prove that the optimization step of the information bottleneck objective could be rewritten into the self-attention form. So in some sense, self-attention enables the trinity of the visual grouping, information bottleneck, and robust generalization. In the reality, vision transformers adopt the multi-head attention designs, which could be broadly viewed as a mixture of the information bottlenecks. As a result, how to aggregate information from the different heads and further strengthen the above grouping phenomena matters. So to this end, so we come up with a novel fully attention design where we improve the channel processing block of the conventional vision transformers. So here we show that self-attention is indeed helpful for the robustness. But what is missing for the current vision transformer backbone is we can say that for the current vision transformer backbones, for the token mixing, for the spatial space, it uses self-attentions to aggregate the information. But for the channel processing part, it directly uses MLP to do it. So it's not uses the self-attentions to aggregate the information from the different bottleneck as we mentioned above. So here is we introduce an attention-based rewriting vectors which promote more informative channels by giving large weight. So this design consider different channels more dramatically and holistically compared to the original like MLP block. Therefore, better leverage the grouping and the information bottleneck like properties of each self-attention head. So on the other side, like simplify it is like we find that the self-attention already exists in the token mixing, but it does not exist in the channel processing. So in order to further improve the robustness, we should like make both part as the self-attention formulations. So that is the head of ideas. So however, so the vanilla self-attention serve from the two major drawbacks. So if we directly apply the attentions, the first drawback is the computational overhead. So the self-attention is quadratically proportional to the channel dimensions. And for the model, like a pyramid model architecture designs, the channel dimension becomes larger and larger at the top stage. So consequently, directly apply the self-attention will cause a large computational overhead. So this is the reason why if we directly apply the self-attention here for the channel part, it will introduce this d squared time complexities to the channel dimensions. So d is the dimension of the channel. So another drawback of the directly apply the self-attention is that another drawback of the self-attention is it will contribute to the lower parameter efficiency. In the conventional self-attention modules, the attention distribution of the attention weight is sharped through the softmax operation. So consequently, only a part of the channels could be contributed to the representation learnings, as most of the channels are diminished by being multiplied with a small attention weight. So this softmax strategies introduces the low computational propulsion as well. So in order to further improve this two aspect, so we propose two improvement for the conventional self-attention blocks. So first, so instead of calculating the correlated matrix between the token features, we first generate a token prototypes by average over the channel dimensions. So intuitively, this feature can aggregate all channel informations for each spatial positions represented by the tokens. Thus, it is informative to calculate the correlation matrix. So secondly, instead of applying the softmax functions, here we use single mode functions for normalizing the attention width and then multiply it with the token features instead of using the matrix multiplication to aggregate the channel informations. So intuitively, we do not force the channels to select only a few of the important tokens features, but we reweighting each channels based on the spatial correlations. So indeed, the channel features are typically considered as independent. A channel with large values should not restant the importance of the other channels. So that's the reason here why we use the sigma mode here. So by using this kind of improvement, so we can reduce the large computational overhead, and we can also achieve a much efficiency with only small amount of parameters. So here is the result. We can see that our method achieve a significantly improvement in terms of the robustness, but at the same time, the models binary accuracy, which test on the clean data, also improved as well. So for example, our model could achieve around 35 MCE with only 16.7 million parameters. And we can see that by using like our like improved like architectures, which we call the fun here, we can see the clearly like clustering and visual grouping for the like image. So note that all of these things are on the classification task. We do not have the segmentation maps. So this cluster are like indeed a property of the vision transformer like design. And also like we apply it into the different downstream tasks, such as the segmentation and object detection as well. So we can see that like our method can also achieve like the higher robustness related to that. So we already talked about the architecture. So what else can we consider to improve the robustness? So here, let's consider about the training algorithms. So let's zoom out to the data and architecture about the training steps. So the reason why like the model is not robust against the test data which share the different distribution of the training data is because if the training data is located in this like distribution, but if the test data is located in the unexplored like regions, we cannot know like what is the label it looks like, right? Because you do not provide enough signals. So to solve these problems, the like a simple but effective way is we leverage the data augmentation. So the high-level idea is like we can increase the diversity of the training data by using these like augmentation strategies. So this is the high-level idea of the algorithm mix. So for the algorithm mix, it proposed to do the cascade like augmentation vertically and horizontally. So it can produce new images without like varying too far from the original images. So in this way, it can generate diverse like augmented images to explore more regions. And it indeed shows the robustness improvement. But what is missing here is like, if you do the augmentations, for some regions, which is like hard can be, so not all the regions can be sampled like equally. So there are some regions which is not really easy to be sampled. So we call it as the hardness regions. So that's like if we directly increase the diversity, it cannot like it indeed improves the like robustness, but there still has like a large space to which we can explore for the unexplored like regions. So here is like we call that as the hardness region. So here we propose like a method which we unify the like diversity and the hardness together to further improve the robustness of the current like deep learning algorithms. So the idea is like simple. So for the original like algorithms, so it do the cascade like augmentation vertically and horizontally. So here, instead of like do the random like sample of the parameters of this like augmentations, we here to do the adversarially to do the combinations. So in this way, it's like we can use this randomness to keep the diversity, but at the same time, so we can leverage this adversary like parameters to help us to find the hardness regions, which is harder to explore by directly using simple sampling strategies. So by combining these tools, like we indeed like find that it can improve the like models robustness. Okay, so we already talked about the like different perspectives among the training stage in terms of the architectures and also in terms of the like training algorithms. So next, let's think about like at the test stage, how can we improve the robustness? So in the test stage, what we have like is like we have a pre-trained models, but we cannot access the training data and the corresponding labels. The only thing we have is the test image, a single test images, and pre-trained models, and we want to do the predictions. So in these settings, how can we improve the robustness? It's like questions we want to address. Note that it's also aligned with the recently proposed concept of the foundation models, which trains on the large data set and parameters and show the great representation abilities. So here we are interestingly given this foundation models, how can we improve their robustness in a zero-shot manners? So to study these problems, we select the well-known foundation model CLIP as an example. So for CLIP, it has the open set properties, which is semantically rich foundation models. Additionally, it also shows a great zero-shot robustness to many distribution benchmarks. So in order to do it, let's first see how CLIP works. So for the CLIP, different from the traditional classification, you only train one model and do the prediction. For the CLIP, it has the two branch. So it has an image branch, which get image representation. And also it has a text encoder branch, which it can embed the text as a feature representation. So for the CLIP models, it uses the contrastive loss to train the models. So after training, it can directly apply to the classification task. So the way to apply it is we provide a template, which we call it as prompt. And for example, if we want to do the ImageNet classification, so we directly provide the 1000 class into this prompt. So it's like a photo of a plant, a photo of car, or photo of dog. So we put all of these things into the text encoders, and then we can get the 1000 feature representation of the different, in terms of the different class. And then given the images, we also get images representation. So we directly calculate the similarity among that. And then we find the one which the highest similarities as the targeted labels. So in this way, we can say that it indeed has the open set properties, which means that we can arbitrarily change the targeted labels, and it can also work. And some experiment shows that it indeed improved the robustness since it trained on a huge amount of image and text pairs. So because here we consider the test stage, how can we improve this a robustness of the foundation model? So a straightforward way is to do the test time optimization. So for the test time optimization, since we do not have the training data and the labels, so it is important to design the unsupervised loss functions to improve the robustness. So here, similarly motivated by some previous works, the consistency loss has been applied to achieve these goals in these domains. So for example, for the TENT, which is a standard test time optimization method, given a batch images, it optimizes the batch normalization statistics to make the different batch has a consistent entropy to improve the robustness. So here is we know so in order to conduct this test time optimization, two parts is first is the loss function. We know we should use some consistent loss. Another part is what should we optimize. So some researchers shows that if we directly update the models parameters of these foundation models, it will overfit to the downstream task, and it will lose the good robust feature representations which learned from trained by the huge amount of data. So here we can see that if we directly train the language model, train the foundation model CLIP on the image classification training data, and update the model parameters, and we can say that the robustness drops a lot. So it means that how to select the parameters to optimize is really important. So here we show that we cannot directly tune the parameters of the model itself. So we need to say what else can we update. So in order to solve this, let's zoom out to see the whole pipeline. We can say that beyond the model itself, another really important component for this CLIP style model is it can provide a prompt, a template. For example, this is a photo of Earth, and some researchers shows that this template indeed influences the model's performance a lot. For example, if this is a flower images, so if we provide the like a template as like we add a type of flowers in the end of the template, we can see that the performance will improve a lot. So it shows that this template is also the key to in terms of the performance of this like clip style foundation models. So it motivates us to instead of update the model parameters because it will hurt the like performance. Can we think about update the like prompt to like achieve the better robustness of the foundation model? So motivated by these things, we propose like our method, which we call it as test time prompt tuning for zero-shot generations. So the idea here is like we directly optimize the prompt to encourage the consistency predictions. And since we want to leverage the consistent loss, and we assume we only have a single images, so we need to have some other like things to provide us some information to do the consistency, because only single images we cannot do the consistency, right? We need to have multiple images, and then we can apply the consistent loss. So a simple way to do it is like we can do the augmentations, and then we augment the images into the different like views, and then we hope the feature representation will regardless of the different views, and in this way it will achieve robust like feature representations and improve the model performance. So simply like motivated by these two parts, we propose like our method. One is like we hope to optimize the prompt, and by giving the different like augmented view of the input images, we hope to optimize the prompt to make them the consistent. And then here we optimize a self-entropy loss to make them consistency. And by this ways, like we can achieve like the better robustness, because the resulting feature representation will like regardless of the different viewpoint. And the result also shows that indeed like our model can achieve like high robustness by like using this method. And so last part of this robustness discussion is like, so now we talk a lot, it's mainly on the 2D space, but we are living in the 3D world. As 3D becomes more and more important, such as autonomous driving use the LiDAR to scan the object to get the 3D information. We also need to think about the robustness on 3D part as well. So based on this, like we propose like a robustness benchmark on the 3Ds, and we release the data set and the code. So welcome to participate in the like challenges in the 3D robustness domain. So maybe we can stop here to answer some questions for this topic.
Maybe anyone else is not asking. I wanted to ask about the clean data performance. Like I guess this was last slide. Like maybe I didn't get a chance to glance over it, but that's the first column, right?
Oh, you mean for this test time optimization method?
Yeah, because clip doesn't have like great zero-shot accuracy. Like the 58%.
Yeah, this is the like clean performance on the original image. So the thing here is like because for the test time optimization, the only thing you have is the single input. So it's no matter it is belongs to the standard like a clean set of the image net, or it belongs to the robust set. You will view them like consistently. So here is like we can consistently like improve the result. But for the robustness like benchmark, it will improve like more.
Yeah, but even the clean one is improved from 58 to 64.
Yes, indeed. Yeah.
I see. That's because of like mainly just the 16 shot.
Yeah, it's we cannot call it as maybe 16 shot because it is still like the test time settings, but because we don't want to argue it as the few shot settings, because we do not know the like label informations, or even we do not have like this like data. But yeah, you can view it as similar to the few shot, but it's not strictly in the same concept. Yeah.
I see. Got it. Thank you.
Okay, so let's move to the next part. So it's about like privacy. So here what we are concerned about is like we want to consider more about the privacy in the practical. For example, the privacy at scale. So many researchers in this privacy domain are largely focused on the like non-deep learning settings or even the shadow like deep learning models and on the simple data set. So here we want to consider if we want to apply the DP into the real world settings, which is like this foundation models, what should we do? Like what should we do to achieve the like DP guarantees for the large scale data set or even for the large scale models? So a standard ways to achieve the like a DP is like we can apply the DP SGD, which is really like a well-known method in the privacy domain. But we can say that the problems of like this DP method is like it will like the privacy like budget will be proportional to the number of the parameters. So if the number of the model parameter becomes larger, then you need to have like the noising will dominate for the gradient. So it's not really easy for you to train the models. So in order to apply this DP at the large scale networks, so what we should do is like we need to think about ways to reducing the trainable parameters. Also, another thing we show that since like if the model's parameters become larger, so the gradient will provide less informative information for you to train like meaningful feature representations. So here is like we argue that transfer learning settings is also really important to like apply the DP on the large scale data set. So for example, here we refer like we need to train like good models on some like non-private like pre-train like data. And after these things, we can fine tune like our models on the like private like crops. So in summary, like in this work, we propose this like parameter efficient transfer learnings. So it consists with two components. The first is like we need to do some efficient training, which we want to reduce the trainable parameters. And at the same time, so we need to leverage the transfer learning settings to get a robust like representation at first. So based on to achieve these goals, like a simple way is also motivated by many of the previous like works I talked is like we can do some like parameter efficient training. So we can do the like prompt tunings. So instead of do the prompt tuning, a way to apply the prompt tuning in this like a standard networks is like we can introduce adapters, which we incorporate additional like models into the current neural networks. And then what we are doing is like doing the like when we want to apply it into the private crops, we only need to update these adapters and fix the other parameters to make it adapter to the private data set with the DP guarantees, but at the same time with higher like utility and privacy trade-offs. And we do some like a simple experiment, and we indeed show that this adapter-based like a parameter efficient training, so indeed like can achieve really good performance. And if we apply it into the ImageNet settings, and even for the vision transformers, it indeed achieve like a little bit like a higher like accuracies. So next part, in the final of this talk, I want to talk something about the social impact. And since it becomes more and more important with the emerging of the like language models. So here we take the language model as an examples because it is another type of the foundation models, and it becomes more and more important in the like NLP and even in the other domains as a like a bridge to connect the language with the other representation such as image, point color, and so on. So here we show that the language models can apply to the different downstream tasks, and nowadays the size of the language model have become bigger and bigger, and it achieves really powerful abilities, such as we can use it to automatically generate the code, or we can use it to do the translation and so on. But one problem of the current language models is it will also generate some toxic language. For example, if we giving a prompt, we can say that for the current language models, it will generate some F word and or even toxic language, which will hurtful the social impact of the deep learning. So in order to solve it, we want to think how can we detoxify the language models. So here, we propose a training based method to do the detoxification of these large scale language models. So the benefit of our algorithm is we don't want to rely on any external data. So we only think about because the language models can generate data. So we are thinking how can we do the self pipelines to make it improve the toxicities. And also we found we also need to do the parameter efficient data efficient training. Because we don't want to use a huge amount of resources to do the detoxifications, because it will also cause some other issues as well. And so in order to achieve it, this is the pipeline of our self-training pipeline. So what we can say that what we are doing is so first given some initial prompt, what we can do is we can feed it into the language models, and then it can generate a huge amount of data. And what we are doing is we use this data and we fill it into some toxicity classifiers, and then we can identify some group of data which has a lower toxicity. And then we use this data to construct the prompts. And we can know that by using these prompts, it will result in the low toxicity. It will result in the language model to generate the low toxicity data. And then we use this non-toxicity data to further fine-tune our models to make it detoxify the language models. And through these pipelines, we can our experiment shows that we can generate a more diverse, and we can do some flexible design of the prompts to achieve the better efficiency of the detoxifications. So here is some examples. We can show that our method named as SGATE, and we can say that SGATE can outperform the baselines with large margins, but with less training data than the standard domain adaptive training pipeline, which they leverage existing non-toxic data to update their model parameters. And we show that by using the self-generated data, because it located in the high density regions, so it will be much efficient to help your model to do the detoxifications. And we also found that a little bit sad news is that when we apply the method into the large scale language models, here we apply it into the over 500 billion language models, which named as Megatron. So we found that the language model, our method will become less effective, because it is more challenging to detoxify the large language model. So in order to efficiently detoxify the large language models, so we may need more training epochs or even more training data to do the detoxifications. So it is so how to require less training epochs or requires less data to detect large language model is still an open research problems in this domain. And also, we can say that even though the toxicity can be decreased, but the publicity, which you can view as the accuracy on the standard data set, will be increased because it makes your model fit more into the non-toxic regions. So it will also hurt the performance located in the original distributions. So indeed, we show there is a publicity and the toxicity trade-off. So to further improve it, we leverage the privacy, introduced parameter efficient trainings to do it. And we found that when we add adapter into the whole pipelines and we only update the adapter's parameters, it will not only improve the parameters efficient trainings, but it will also mitigate the trade-off between the publicity and toxicity. So this is some result. After do the detoxification, we can see that the models generate more less toxicity data. And here is another examples. So in the end, let me conclude at this moment, because I also hope to leave some time for discussion. So in this talk, we only talk about the ways a tiny step towards to a socially responsible machine learning from these three aspects as robustness, privacy, and social impact. But indeed, if we want to achieve a really socially responsible machine learning, there are many other perspectives we also need to consider. So we are still a long way to go, and I hope this talk can give you a brief insight of a tiny step towards to this socially responsible ML system. Yeah, thanks.
Thanks, Chaowei, for the amazing talk. Any questions?
I have a question.
Go ahead, say.
Thank you very much for the very interesting talk. So you mentioned these three interesting pillars for responsible AI, and they're each very interesting, but conjunction of all of them composing all these aspects together, do you see any trade-off between these things, or do you think they can help each other mostly? And what is the state of research on combining these different aspects of responsible AI?
Yeah, this is, I think, a really good questions. And indeed, we need to combine this all aspects together and bring the researchers from the different aspects together into building this socially responsible machine learning systems. So in terms of the trade-offs, indeed, so there is some trade-offs. So for example, if you do the privacy, and we found if you do the DPSJD on the, for example, the long tail distributions, so the performance will be hurt a lot. So original, for example, even on the long tail distributions, if you can design a good algorithms, so the performance drop is not such high as the low tail labels. But if you apply the DP, because it will each data as individuals and keep the privacies, DP privacies, and indeed the performance will become much more severe. And also for the social impact, for example, if you want to do the detoxifications, it will also hurt the publicities, will hurt the general performance. You can view it as will hurt the robustness of the models. So indeed, there exists some trade-off, but how to preserve the good things is indeed what we need for the community. Take our for example fun as examples, which I introduced before. So we want to achieve the better robustness, but at the same time we don't want the clean performance drops. So in this way, we design this fully attentional networks, and we show that it improves the robustness a lot, but at the same time it also improves the clean performance. So that is like what we are really like a pursue. But whether there is a free lunch or not, we are not really sure. So it's indeed needed to bring the different like expert from the different areas together to like address these problems.
I see. Yeah, thank you very much.
I also had a question, like a bit more on the technical end. So in the toxicity setting, like the precise question I wanted to ask was like, what was the motivation to use synthetic data, like the data from the generative models? Because I believe because the real data also must have the same, like you could have also gotten like the training signal or like these set of like again tokens or sentences that have like, because the model learned that from the real data itself, that signal must be there in the real data. So is there like a particular benefit by doing it the way you did?
Yes, that's a good question. So indeed, like the reason why we use the like self-generated data is like we want to make it more efficiently. So if you can definitely use the real world data and you can directly like, for example, you filter it and you generate a corpus of the non-toxic data, which from the real data, that is what existing baseline doing. So, and compared with this methods, if we use our like a language model to generate the synthetic data by itself, it will be much efficient. So the reason is like the data which we generate is located in the high density regions. So it is more like a fit for the current models, what you want to like optimize, right? So then in this way, like you can only use a small amount of like data and you can achieve the comparable like performance, which used with large like external like data from the real world. And another perspective why we can do that is because the current language model is super powerful. It can indeed generate the like data which preserve the high like like a lower like probability, which means that it can generate like high quality data, which is similar to the real data. So you can think is if it cannot generate the like if the generated data is not similar to the real data, for example, it in the image domain, if it generated the blur images, when you train on these blur images, it will definitely hurt the like model's performance. But as the model become like super and super powerful, so due to the large data set and like large parameters, indeed now it has the opportunities to leverage the data generated by the model itself to improve the model's qualities.
Yeah, that I totally agree that even in vision, it is doable that you can get high fidelity samples. Just to follow up on that, like I think like if you use like really big language models, you get this like again qualities in both sense. Like I'm not sure what is the equivalent of fidelity for language models, but that could be like coherence in sentences generates. But then there is also this coverage of a distribution. Like the more generative model can cover high density regions, so but it will always miss some sort of some pattern of toxic sentences that it just didn't pick up from the training set. It has no idea about that.
Yes, that's a really like a good question. So in order to achieve this, like so what we are doing is like we to do the like top like a top P like a sampling. So we select specific sampling strategies which encourage to generate like as diverse data as it could. So in this way, we found that it will like also achieve the we measure the diversity actually. So like distinguish the two distinct like 3 or distinct 5. So that is some like diversity measurement. And we found like our model indeed can like achieve like the performance is not worse. Yeah, so it can indeed generate some like diverse. Yeah, with the carefully like design prompts. But yeah.
Yeah, I think it's like the better generative models we develop, the more it will improve. So yeah, it's sort of like a feedback loop.
Yeah, because here we are not directly use the data generated by the language models to train the model. We are using the data and generated by the language model, and then we construct the prompt by using this data. And so we can like control the diversity of the prompt. And in this way, like we can control the diversity of the data, which will be further generated by the language model. So it's not like only one step, it's the content like multi-step. Yeah.
Got it. Thank you. Do you have any other question? All right, and in that case, let's thank our speaker again. And yeah, thanks again, Chaowei, for the wonderful talk. And yeah, see you everyone next week.
Yeah, thank you.
Thank you.